Why is it so difficult to make an atomic bomb? Well, it turns out that the really hard part is the materials which will undergo fission, which will not only undergo fission, but which will then generate neutrons to create a fission chain reaction. These are called fissile materials, and there are only 4 of them. On this whole table behind me, with the 3,600 squares, there are only 4 squares which can be used to make a nuclear weapon or a reactor. And they are 2 isotopes of uranium and 2 isotopes of plutonium. The plutonium isotope we're all familiar with is plutonium-239. But plutonium-241 is also a fissile material. It's made from plutonium-239, so there's really no point going beyond 239 when you hit something that's fissile. The other 2 isotopes are more interesting because they're 2 isotopes of uranium, one of which occurs in nature, uranium-235, and the other one, uranium-233, doesn't occur in nature, but you can make it from thorium. Now, thorium is an element that's 3 times more abundant on Earth than uranium is, so potentially it's an even longer term fuel source for nuclear energy. The other interesting thing about thorium is that you can actually generate energy in a subcritical reactor. That means you don't have a self-sustaining nuclear reaction going on. Instead, you have a subcritical core of the thorium, and when you subject that to bombardment with neutrons, it is transmuted into uranium-233, which then undergoes fission. If you think that a nuclear reactor must be critical from the beginning, then I have an old document to show you to help you overcome that prejudice. This is Leo Szilard's 1934 patent on a nuclear reactor. And you see, it starts with an accelerator. He uses an electron accelerator called the cathode ray tube, accelerates some deuterium, accelerates the electrons toward a deuterium target to produce neutrons, which will then make the surrounding fuel go critical. This kind of reactor has its advantages because it is more controllable than a critical reactor. All that you have to do to shut this reactor down is turn off the accelerator and it's done. Now, you might ask, well, how in the world are you going to get neutrons except in a reactor with uranium or plutonium already in it? Well, it turns out there's another way. There's a phenomenon called spallation. Spallation is a term the nuclear physicists borrowed from geology. If you've ever seen someone knapping flint, where they strike the flint with a rock and little flakes of flint come off so that they can shape the remaining flint into an arrowhead or something like that, that is an example of spallation. Now, nuclear spallation works a little bit differently. Basically, the only spallation accelerator I've ever seen was at Oak Ridge, Tennessee. And in this one, they start with negatively charged hydrogen ions. And they accelerate them in a linear accelerator to very high speeds, about 90% of the speed of light. And then they capture them in a storage ring. This is like an accelerator, but it doesn't have to actually do any further acceleration. it just bends the path of flight of the protons. They pass the hydrogen ion beam through metal foils to strip off the electrons, and then they have protons circulating in the storage ring. And they release protons from the storage ring into a vat of liquid mercury. And what happens is that these things come flying in there really hard. And when they hit the targets, which are mercury nuclei, they cause a phenomenon of spallation, where a number of neutrons and protons fly off of the nucleus. Now the protons are captured in the mercury because they're electrically charged. It's easy to capture them. But the neutrons continue, and substantial flux of high-energy neutrons can be generated in this way. One could use an accelerator, a neutron generator by spallation, in order to power a subcritical nuclear reactor fueled with thorium. Now, eventually it wouldn't be subcritical anymore because these reactors generate more fuel than they use. So they would eventually build up enough uranium-233 that you would actually get a self-sustaining nuclear reaction. But you could get it started with only thorium and a powerful neutron source. A thorium breeder reactor was operated at Oak Ridge, Tennessee during the 1960s, so the proof of concept has already been done. But when it came time to spend more money to generate designs for commercial nuclear reactors like this, the Navy objected. The Navy was in the process of designing and building their boomers. These are the nuclear missile submarines that lurk under the oceans, carrying a very large amount of nuclear firepower, which can be delivered anywhere they want. And they thought they were going to need a lot of plutonium in order to make all the warheads for all these missiles. So they didn't like the thorium cycle because it doesn't generate plutonium. It generates other things, but not plutonium. So they went with the uranium-fueled reactors instead, with the idea that the plutonium produced in them could be purified and used to make nuclear weapons. Now, in fact, that never happened because our country has not been able to get their heads around reprocessing nuclear fuel, so all that plutonium that's been made in all those power reactors is still sitting at the power reactor in large vessels, presumably forever, since our government is afraid to transport them from there to some more permanent storage space. So that's why it's hard to make nuclear weapons, because there are only 4 isotopes which are fissile, and the only one that's naturally occurring is uranium-235. All the others have to be created in a nuclear reactor and then purified chemically from an extremely radioactive mixture. This is a very challenging chemical project.